Hello, everyone. I'm your host, Naomi Angran, welcoming you back to Good Morning OSU, your favorite morning news show. As you all know, or at least I hope you should know, April 22nd was Earth Day. To celebrate, we have a special program today with a group of engineers from the Ohio State University Civil Engineering Department. Introduce yourselves to our lovely audience.
Hi, I'm Sanjay.
Hi, I'm Sean.
Hi, I'm Alyssa.
As another surprise for you guys, I'm an engineer on their team too. Today, we're going to speak about our recent research into wood waste and green concrete. So grab yourself a cup of coffee, preferably iced, or even a cup of ice cream. Then sit back, relax, and enjoy the show. In the US alone, between the years of 1969 to 2004, the amount of wood waste produced quadrupled to 63 million tons per year. That's about the amount that it would take to fill up 1.4 million 12 by 24 swimming pools that are 5 feet deep. That's an insane amount of waste. Sadly, wood waste is still on the rise to this day, so our group decided to do something about it by exploring the use of the wood in making green concrete. Before conducting any tests ourselves, we familiarized ourselves with the experiments other people did to determine how wood would affect the properties of the concrete. The main issues that resulted were that the wood decreased workability and replacements greater than 8% led to compressive strength issues. All of this research led to our final hypothesis that the 5% wood mix would be more durable but weaker and less workable than a control mix without wooden fine aggregates. All right, I think the audience heard enough of my voice, so I'll pass it to Sean to talk about our materials and testing methods.
So for our experiment, we created two concrete mixes, mix one, our control mix, and mix two. The ingredients for mix one were Portland cement or Quikrete number 57P gravel, which was the coarse aggregate, concrete sand, which was the fine aggregate, and water. The ingredients for mix two were the same as mix one, except for the addition of wood shavings. After gathering all the ingredients, we mixed them together until we had a homogeneous mix. And then we performed the slump test, which looks at the workability of the mix. And we performed the pressure method air content test, which looks at the entrained air in the mix. Both mixes were then put into 3 4x8 cylinder molds to set and cure for a total of 7 days. After retrieving the cylinders, we performed the last two tests, the resistivity test, which looks at the durability of concrete with respect to corrosion, and the compressive strength test, which looks at the overall strength of the concrete. And here is a picture of us preparing the cylinders for the resistivity test. As you can see in the picture, we wrap the cylinders in damp paper towels in order to keep the surface more moist before starting the test.
So here is a video of the electrical resistivity tests that we conducted. As you can see, the prongs of resistivity meter are lined up with the straight quadrant lines that were drawn on the cylinder. This allowed us to measure 4 different points on the cylinder. And this is a video of the compressive strength tests for the control mix. In this video, the compression machine is gradually increasing the load on the cylinder until it reaches a max load right before fracture. About 2/3 of the way through this video, you'd see right about now that the cylinder starts to crack at its max load, and you can see that it's broken in multiple areas.
All right, Alyssa, can you tell us more about the results of the experiment?
Yes, I can. So for the results of the experiment, as you can see in the figure on the right, the control mix samples had a greater resistivity than the 5% wood mix samples. This alludes to that the 5% wood mixture was more resistant to conductivity, and therefore that alluded to as well that it had a higher durability. In the next slide, you can see some photos of what the cylinders looked like post-compression. So for the first two that you see on the left, the 5% mixture showed a certain degree of post-compression fractures. And then for this last photo on the right, the control cylinder post-compression, you can see a lot of the voids that we noticed within the cylinder before the compression, and then the fracture point at the bottom.
All right, and how did the results compare to our hypothesis?
Yeah, so as per the hypothesis, the 5% wood mix was indeed more durable, but less workable than the control mix without the wooden fine aggregates. And the 5% wood mix was too unworkable and required more water. And you could see this in the next slide when you compare the workability of the control mix and the 5% wood mix. If you can scroll to the next one. Yeah, so the one on the left, it was pretty workable and, you know, needed a bit more mixing in terms of, in retrospect, the voids that we saw in the cylinders, but the one on the right without the water added for the 5% wood mix, it was completely unworkable. It was hard to kind of get it to coagulate fully.
Sanjay, can you tell us more about what our results tell us?
Yeah, so our results, we looked at workability, and the loss of workability in the wood mix is mainly due to the increase in friction between the wood particles, rocks, and sand. This resistance is created when acting surfaces are rubbing up against each other, which then cause the mixture to lose its flowiness. We then looked at the electrical resistivity test, and it relates how easily ions can move around inside the concrete. And this lower resistivity in the 5% wood mix meant that the ions struggled to move around in the mixture, making it more durable. Both samples, in fact, allowed a high penetrability level of chloride ions, but the 5% wood mixture was slightly less in the base mix. Since the ions were not able to move as freely in the wood mixture, concrete cylinder showed an increased resistivity, which directly correlates to an increased durability. When we talk about durability, it means that this concrete cylinder will be able to perform and withhold the properties of the design over a longer period of time and under harsher conditions. Our experiment results, we were limited on time, and we also struggled to get the mix weights in order. So it was tough to get a third mixture or a fourth mixture with higher wood percentages into molds. It would have been nice to test a 2.5, 5, 7.5, and 10% mix to determine which would perform the best. According to some research that our group did, the ideal replacement would be 15% wood to get maximum strength among the wood mixes, but less than an 8% addition of wood would be the most ideal for retaining all the important properties of the mix, and that would ensure an increase in durability, but decreased workability and compressive strength.
And how can we apply everything that we learned to the construction world?
So potential mass use of wood additives in our concrete mix rely on a few factors. So using wood as a substitute for a fine aggregate will limit the need for excessive extraction of natural rocks. Using recycled aggregate would also cost a bit more, but it would lessen the mass transportation of aggregates, and this would lessen the environmental impact. Sustainable practices aren't fairly common, but there is still significant testing to be required to ensure that these mixes would meet specifications for concrete application. Further testing to be done is that we could potentially replace the fine and cement at the same time. We could also evaluate how wood shaving size and shape change the properties of the concrete performance. And lastly, they're looking at adjusting wood properties such as humidity, moisture, the type of tree, and treatment done to see the effects on the concrete mixture.
All right, that's all we have for you guys. Thank you for listening and joining in. Tune in next week where we'll talk about the water crisis on campus.